Thanks. I'm really happy to be here. I hope that Dick will take the time well and allot me half an hour exactly when I'll need more of it. So I'm actually going to talk about structure in theoretical computer science, just not to get into trouble. And some of it, I would say, surprising structure, and the insights that come with it. Many talks here the last 3 days, which were absolutely fascinating, were mainly about the, colonialist power, TCS trying to take over the world, quite successfully. In fact, Dick asked me to show you some picture of the Simons Institute heading this plan, which I'm sure you've seen Calvin Hall, and in it the plan is being renovated now, the very interactive lobby, and there is the, for some reason they call it the peace room, mainly because they come in peace, and they start looking at first conquering the sequencing part of biology. Here you see the other directors taking over statistical mechanics and quantum computing, and of course economics is not left behind, the Nash equilibria and price of anarchy, and where is this guy? Even sex, so I'm sure you'll see Christos all over the world there. Of course, we bring to these people, these natives of this strange land, our culture that they are usually happy with, algorithms, modeling, lower bounds, etc. And generally, actually, they like us. And there are some descendants. I have some rare footage here of some. You may recognize it. Oops. How does it go? Maybe I don't have it. Okay, I don't have it. Those who would see the movie, who saw the movie, would know. And now I don't have anything. All right, Luca. This is okay. Go. Luca will tell you later. Okay, so what what are we bringing that mathematics didn't bring? I'd say that this was raised before. Wigner asked about the unreasonable effectiveness of mathematics in the sciences, which we neither understand nor deserve. I don't know about the deserve issue, but sometimes it is mysterious. In the case of theoretical computer science, I would say that we understand. There are so many information processes in the sciences. At least this is something we understand about, and that's usually where we contribute. But I'm not going to talk about this aspects of the field. I rather want to concentrate on the core of the field, on the core and the many sub-areas of the core and their interconnectivity. This is like the dungeon of theoretical computer science, where we, where we sometimes pick out, and some members give to us a theory of learning or a theory of cryptography or things like that actually propagate out. So I want to talk about this and structure in this core of TCS, and of course about the lots of questions that we cannot answer yet. So here are 2 slides about this structure that I'll later elaborate on, but you can just watch them and then sort of relax. We look at the world much like physicists, I'd say. I mean, there's nature out there, and these stars happen to be computational problems, and they are really weird and bizarre and are all over the place. And they, just pick your favorite. They come from different motivations. And somehow, magically, despite the huge difference between them, we find that they classify themselves into really, really few classes. And in these classes, they are, more or less equivalent. So really, there are very, very few different types of problems, despite the potential, infinitude of them. And of course, to understand this, you need to understand algorithms, analyze them. And what I'll insist on, talk a lot about, is reductions and completeness that play a huge role in this structure. But this is just problems, single problems that a single computer is trying to solve. Turns out that even if you look at much more complex domains like cryptographic problems, where there are many players with different interests and privacy and all sorts of bizarre scenarios that have to do with playing poker on the telephone and signing digitally and zero knowledge and whatever you want. You look at all these amazing, much more complex world, and also there you find amazing structure. Turns out that they all fall in a class which is roughly equivalent, and there is, just a subworld which where the problems are also equivalent. Here the names, by the way, of course, cryptographers are more imaginative than complexity theorists, and the classes have better names. Also there you have complete problems, and also there basically the same story happens. So what I want to talk about is some of this structure and, why do we deserve it, or why does it happen? So I'll talk about 5 themes, like in this movie. There'll be 4 happy stories and 1 sad one. This is my world. And I'll talk about high-level structure, and of course, lots of the work to do is about, once you understand high-level structure, get to understand lower level, like in physics. And like everyone else, the origins also of structure start with Turing. I'm following a long tradition of speakers who started with Turing, the father of our field. In this paper, to those who don't know and are young, are doing their PhD, that's the model of a PhD thesis. That was his PhD thesis. He proposed this extremely simple model of a computational device, and this did everything. I mean, I'll elaborate on this. But the effects of this are just growing every day, and everyone anywhere in the world is feeling them. And I want to stress that this is the product of a very good theory. Les Valiant told us in the first lecture about Ramon Cajal and his attack on the theories. I think, I'm wondering how he would react to this. So it just, it's a math paper, and look at what happened. What happened? Technology. So computing revolution. Why did it happen? Because the model is so simple, and so your operations so simple and local that they can be implemented by very simple logical devices. And these logical devices have many, many physical realizations, and then you build computers. Turing also built them. Science. Well, the basic idea that you look at processes in which simple and local steps, develop, evolve in complex structure, that's what Turing called computation. And in fact, he demonstrated by bits on computers, but took his cue from neurons in the brain, from person computing. And then the same processes, happens in atoms in matter and cells in living tissues, individuals in populations. It happens in lots of places, and that's the reason that a simple device like this can simulate lots of these processes, the Church-Turing thesis. And finally, the math. This is a formal mathematical model. This will be the part that we'll, most use in this talk. It's a mathematical model. So now we can study it mathematically. This tells you exactly what a basic step is and what a memory unit is. And now you can just do math with it. In our case, analyze algorithms, prove lower bounds, and so on. And in fact, Turing was the first to do it. He first applied this to say, here is a very rough structure of our universe. The structure is just dividing it, first of all, to solvable and unsolvable problems. Not everything is solvable. In fact, very basic problems are unsolvable, like testing whether a computer program is correct, or like testing whether a statement in logic is provable. And then people took over and proved the same for basic other questions, like in mathematics, testing whether an equation has a solution. Or in biology or physics, testing whether a system, giving precisely the rules for its evolution, whether it has some long-term property. So this was the first rough structure of the universe. And of course, it's not enough. Solvable problems, we want to know when. And we have to start developing developing computational complexity. Okay, so let's talk about this. And there were 4 happy stories. The first happy story, which will serve me, I mean, I'm sure many are aware of this. Actually, I'm wondering, how many people here do not define themselves as computer scientists? That's great. This is really fantastic. Of course, the Simons Institute defines you as computer scientists, but so we'll serve a crash course on complexity and basically, start looking at these object reductions, which are algorithms translating problems to problems, and much more that I want to develop here. So this will be the classic ones. So we start trying to understand complexity. So which problems do we call hard? Which problems do we call easy? People started playing with problems, let's say graph problems, like two-coloring a graph or finding a shortest path, or problems on formulas, testing whether they are satisfiable by Boolean assignment, problems on integers, like multiplying things. And they developed fast algorithms for them, and actually realized that, so fast algorithms, I mean polynomial in linear time, quadratic time, cubic time. And one important fact that one of the, I'll start with these insights, was this 2 points of view. These algorithms work for every input. So this was the worst case analysis viewpoint, which served us well for a long time and elucidated structure. And the other is the asymptotic viewpoint, that we want to understand performance as data grows. This is very prescient. Actually, we see that data actually grows. It's now big. It will probably be, I think big data is already what happened last year. It will be soon humongous data. It's good to have an asymptotic viewpoint. You see much more what the algorithm is capable of. And as a rough beginning, people formulated the notion of P, of polynomial time, as something that's easy, an easy problem, an efficiently solvable problem. And that, again, was very powerful because it's robust to lots of changes in the model, and that elucidates structure as well. Okay, these are the easy problems, and of course people realize that similar problems, actually very similar looking problem. Another insight, important insight, that 2 problems, when they look very similar, doesn't mean that their complexity is similar. 3-coloring a graph, finding the longest path, solving 3-SAT, doing the opposite of multiplication, factoring. The best algorithms that we know today are exponential time. So are they hard? Well, we don't know. In fact, there's so much we don't know, but that's the most basic thing we don't know. We have no idea. So, but the first observation here is that this dichotomy between polynomial and exponential that was clear we have to face with. And all the coarse graining, the resolution in which we have to look at the world first is distinguishing these 2. So we don't know what are the complexities of this problem, but there's something we do know, which is really amazing. This was the first understanding in the 70s, is that despite the fact that we don't know the complexity of coloring, and we don't know the complexity of, let's say, 3 satisfiability, if we have an algorithm for coloring, then we have an algorithm for satisfiability. And in fact, we also have an algorithm for factoring and for Hamiltonian path. So what's going on? Something must unite these problems if there is such a connection. So what unites them? So let's look at the world again. The problems we mentioned, okay, so there are the easy problems, problems for which you can find solutions, but what about the rest? So it's very tempting to put a circle here and say, yeah, sure, they are exponential time solvable. And the important thing is to insist to have the tightest characterization on the problems at hand. And this is not the tightest. There is something much stronger you can say about all these problems, which is that maybe they are hard to solve, but if I give you a solution, it's very easy to check. And this was a hugely powerful observation. In fact, it's the first time, I would say, that proof, the notion so common in logic, was quantified computationally. It was not me, I see. Quantified computationally. What do I mean by that? That you don't care about the exact syntactic structure of your proof. All you care is that the verifier can read and understand and accept the proof as bug-free in polynomial time. Once you have this, well, these encompass problems we can easily solve. These are problems when you understand, you think about it, these are all the problems we can ever hope to solve, or most of them. Because in most problems we hope to solve, we at least believe that when we see the solution, we'll know it's the right one. So given that this is the informal meaning of these two classes, the question of whether these two classes are the same is a major problem in all the application areas that are generating problems in NP. So how do you deal with this P versus NP question? There was some lucky break that, again, you might wonder whether we deserve it or not. What's the lucky break? Well, this was the first lucky break, that one problem, 3SAT, if we have an algorithm for it, we have an algorithm for the whole class. It is an NP-complete problem. Now, what's the chance of that? You are trying to solve million people or thousands of people or different paths for different motivations are trying to solve different problems. Probably they each need to do their own work. No, the message here is that one problem, if you solve it, you solve them all. That was the first miracle. And the next miracle, this was Cook and Levin, the next miracle a year later by Dick Karp was this miracle. There's another problem like this. Free coloring, the theorem we mentioned before. So this is also NP-complete. If we have an algorithm for it, then we have an algorithm to 3SAT. Now, what's going on? What's the connection between these problems? I'll tell you in a second, but in fact, Dick in his paper, I'm not sure, 21 or 23, Christos. There are lots of problems that are very different that all fall in this class. They all determine the complexity of all problems in all of NP. And if we look today, a few decades later, there are thousands of problems like this. They are all equally easy or equally hard. Now, this is a phenomena that I don't know any other in the sense that it's ubiquitous in science. This is all across the sciences. Sciences of all types have NP-complete problems in them. I don't know what else is common to all these. So there are two questions to ask. Who is proving these theorems? There are thousands of theorems. There must be thousands of papers. And why are there so many problems in so many disciplines that are equivalent? So let's answer the first one. Why are people proving NP-completeness results? Well, I mean, computer scientists, it's clear. This is a certificate of hardness. If you cannot solve, if you cannot design an algorithm, a fast algorithm, that's your excuse. If you did solve it, you'll solve everything else. Why do mathematicians? And mathematicians, I guarantee, prove hundreds of NP-completeness results. Because what it says about structure is not necessarily computational, but it says that there's some structural nastiness in the problem. I'm not going to get into the NP-co-NP story, which is behind this, but just telling you that it is there. And why do biologists, economists, physicists prove NP-completeness results? Because it's some model validation. I mean, if you have a theory about protein folding, that it somehow minimizes energy given the strength of bonds, and you realize it's NP-complete, something is wrong. If you have a similar theory here, something is wrong. So if your model predicts that nature efficiently solves an NP-complete problem, something is wrong. So what are the possibilities? Well, either your model is wrong. Here it's completely wrong because it just finds local optima. Here it's not completely wrong, maybe, but certainly proteins are not all sequences. Maybe for some sequences that never arose in evolution, it solves them efficiently. Or maybe, P equals NP. Well, both things are good. Here, these possibilities tell you that, like the second law of thermodynamics, you should have in the back of your mind, if you are a scientist, another law, namely P different NP. And if your model predicts otherwise, should seriously take it into consideration. And the other one, if you discover anywhere in nature something that you know, is very efficient, maybe more efficient than your laptop. Add it to your laptop. Add it to your notion of P, and that's what we've done with randomness, and we will do if people build quantum computers. So now let's get back to the question of why there are so many NP-complete problems. The short answer is locality of computation. It's not a mystery. It's not by accident. It's because of Turing's definition and the very nature of computation. So let's look at one reduction, a classic reduction from Dick's paper. What's the relationship between coloring graphs and satisfying formula? It's very simple. So what does the reduction have to do? It has to translate, it wants to use an algorithm for coloring in order to solve satisfiability. So it has to translate formulas into graphs. How does it translate large formulas to large graphs? Locally. Formulas are built of gates, and we'll come back to this, are built of gates. And so if you could simulate this by a little graph, then you could simulate a large formula by a large graph. And that's exactly what you do. You construct this, you know, magically. You construct this little graph, and it turns out that whatever colors you assign these X and Y nodes, colors are just, you know, just arbitrary pick colors for truth and false, then this variable will be there all. Once you have a gadget like this, the rest follows. So this is a classic reduction, and many reductions look like this, and they are essentially all NP-complete problems are based on such local reductions. And in fact, that's the reason that it's so easy for scientists all over the world, or all over the sciences, to prove theorems like this. These are the typical reduction, okay? And like I said, that's why if you had an algorithm to color, then you have an algorithm to SAT, and vice versa. Reductions always have bidirectional implication. If SAT is hard, then coloring is hard. So, like I said, what's happening here is happening in lots and lots of problems, lots of local structures arising in whatever, in math and physics and biology, can implement a little gate. Once they can do that, they can simulate computation. Once they can do that, chances are they are NP-complete, except for, of course, the rare cases we can solve. Okay, so that's a story. And actually, given that this is a story, you wonder that there are so many NP-complete problems, and of course, there are so many problems that we can solve. That's a structure we have now elucidated. You wonder what's in the middle here. Actually, there are very few problems we know that are not either. It's really mysterious, especially given Ladner's theorem that tells you that there are infinitely problems in between of different complexities. So somehow they are not natural, and it's very interesting, and it's ongoing work to explain this dichotomy. And I guess these people are close to, at least for constraint satisfaction problems, to say there must be either of this type or this type. So there is an explanation for this structure, which is much, very interesting. So this structure was elucidated because we picked, I would say, the right resolution to determine the next level structure, namely polynomial time reductions here and here. And of course, once you have this structure, you go on and refine. In fact, this is done. You can look at linear time reduction between them. You can look at sub-exponential time reductions here, and people are doing that. So I'm not going to talk about it. Okay, so this was the beginning. This was the crash course. This was what many of you know. So now I want to talk about much more sophisticated structure. Until now, we talked about optimization problems or decision problems. What happened since the 70s? So I want to talk about approximation problems. That's the second vignette. And here, the reductions are going to be much more sophisticated. So the mystery of approximation. What's the mystery of approximation? Of course, we knew, as I said, in the 70s that lots of the problems we want to solve, optimization problems, are NP-hard. We are not going to, well, either we solve them or they are NP-complete, and we can hope to solve them. So that's the nature of problems. They don't go away. So what do you do? Well, you do one of a variety of things, but one of the most basic ones is just try to approximate the optimum. If you can't get it exactly, get it within, factor of 2, within a factor of 10% or better. Try it. And of course, people did, and they did. And actually here, you saw much less structure because for different problems, different hard problems, the approximation ratio that the various algorithms got was, for 3SAT, for example, I mean, if you just take a random assignment, the probability that you satisfy a clause is 7/8, right? There are 3 variables, so it's 7/8. It's very easy to get an 8/7 approximation factor to 3SAT. To other problems, traveling salesman, vertex cover, you get other constant approximations that are worse, and then you move to other problems, and you can't even get constant factors. And it gets worse and worse. And it's also even worse that you don't understand where these numbers are coming from, and you also don't know whether they are the right numbers, because these are just upper bounds. These are just algorithms. So we don't know whether they are good. We can do better. Is there a theory explaining anything? That was the situation, actually, for a long time. And then, 2000, 30 years later, Johann Hastad proved this theorem. For 3SAT, this problem, you cannot beat 7/8. The trivial solution of picking an assignment is random, is optimal. There is nothing better you can do. It's NP hard to improve even by a tiny epsilon. So I want to tell you about this. It's a reduction, actually. So how did it happen? Why did it take so long? So this is a story. Here we have NP hardness of 3SAT, and that's the tightness of its approximation ratio. Look at the time scale. So what happened? What happened in these 30 years? So that's, those of you who, I mean, it's a story, these stories you never believe, how the elephant got its trunk, right? An alligator pulled it. This is, that's a story. So I'm going to tell you this story. I mean, those of you who've never seen it are not going to believe it, because it should look like carp reduction for 3 coloring, right? So what happened? Actually, there was a stepping stone. First, there was a proof that it's hard to approximate with some tiny factor before there was a tight approximation ratio. So this took a decade, and this took two decades. So let me tell you in one slide each about what happened there. Basically, new techniques, completely new techniques had to be developed, and they had to be developed in completely different areas of the core of TCS. And that's an important message I want to mention, and mention again and again. So what happened in this decade? Basically, the main tool that had to be developed is understanding the influences of variables in Boolean functions, or the influence of people in voting schemes, different voting. The motivation was game theoretic and distributed computing, and the tools needed to be analytic. But once they were all in place, a guy like Hastad could take them and actually make this reduction. But they have to happen. What happened here, these 2 decades? Here it's even bizarre, more bizarre, because here what needed to happen is the invention of interactive proof. I'm saying needed to happen, I'm willing to bet on it. I mean, there is no other way I can, well, it's not literally true. It could have happened otherwise, and with hindsight, did happen otherwise. But that's how it happened. So people invented these interactive proofs. Shafi talked about some of them, interactive proofs, multi-prover interactive proofs, probabilistically checkable proofs. They were invented for completely different reasons in cryptography. The techniques to understand them were invented yet again in a completely different area of program checking. And then we started understanding these classes of problems for which you had these interactive proofs, and they turned out, amazingly, to be familiar complexity classes. Here it was p-space, here it was non-deterministic exponential time. Then the connection finally was made to optimization, and this class turned out to be just NP, which meant, essentially, that 3SAT was hard to approximate, at least to some non-trivial factor. So all these things had to happen, and again, I'm putting up this. So these were the first 3 decades, and till this tight in approximability result. Let me tell you in one more slide what happened in the last decade. This, I think, that is my most advanced thing, story, and I assume that not too many people know about it. So at least to some, I'll bring new news. So what happened in the last decade? So by the 2000s, we really, because of this ability to prove hardness of approximation and getting, we were able to get tight in approximability results. We knew for a variety of problems exactly what approximation factor we can achieve efficiently, and even a tiny bit cannot be achieved unless p equals np. So that's amazing. But amazing as it is, you still get weird numbers. Where is the structure in these numbers? Where are the numbers coming from for different problems? And this is what progress we've made in the last decade. It elucidated a single problem, which is a new complete problem. It's called the unique games conjecture, but it's basically a question about the approximation factor you can get for the most basic question in mathematics about linear equations. Why is this so important? The understanding evolved in this decade because one of its culminations, a result by Prasad Raghavendra here at Berkeley, says the following. You want to know these numbers? No problem. In fact, you want to know the optimal approximation algorithm for them? No problem. There is a single algorithm that will do it for all these problems, any problem. You just run it, and it will tell you. It has a little box telling you what the approximation factor will be, and it will achieve it for you. And nothing more is possible unless, well, assuming this is NP-complete, unless P is different than NP. This is amazing understanding of structure. In fact, I would say it's sort of unbelievable. My friend Sanjeev Arora likes to say that about this single universal algorithm. So those of us who tend to get papers to referee, let's start with P different than NP in the title, often, really seriously, they often start by, look, okay, here's, I want to solve 3SAT or some NP-complete problem. What else can I do? Here's an algorithm. It's obviously the best algorithm. Now let's analyze it. It's exponential time. Good. P is different than NP. So this says it's not as ridiculous as it sounded, maybe. Okay. So we have another notion of completeness. Here there is a complete algorithm, and Christos mentioned another complete algorithm, the multiplicative weight algorithm. There we tend to figure out a few algorithms that have some more importance than others in our life. And I want to mention that also the mathematics of all this starts getting, as you saw in the previous slide, more and more sophisticated, and there are really amazing connections to analysis and geometry, and also for the mathematicians. Okay, that's the end of my second vignette. So the next two vignettes, I'm just going to be good. Now I talked for half an hour, Dick, measured on. I'll do the timing. I think it's safer. Okay, don't wait.
I think your time is up.
So another important notion I forgot to mention, but Shafi did it for me, is the adversary. So and we are just ready for the adversary here. So I want to talk about cryptographic problems and structure in cryptographic problems. And again, the story is very elaborate, and I'll just give you a cartoon version of it. So cryptography for us, starting in the 70s, is complexity-based cryptography. I want to stress that, like Turing's theory, the theory, it predated the internet, predated electronic commerce, and in fact enabled them. Without them, it wouldn't evolve. Again, theory. What are the axioms of the theory? That everybody playing is limited in time, and that there are some hard problems, nice hard problems like factoring. And this easy and hard are, because of the asymptotic viewpoint, it's to your scaling. If you see that the key length or on DES or whatever the scheme is increasing, it's because of exactly this reason. Computation power increases, no problem. We'll increase key length so that factoring will be hard enough so that these guys can't solve it. So that's another advantage of the asymptotic view. Okay, these are the axioms. And now comes, the question of why is factoring a useful problem for cryptography? And this is really another insight that I think is absolutely fundamental, and we keep carrying it, is this tension or friendship. I mean, this complicated relationship between information theory and complexity theory. So in this case, it's manifests itself in a very simple way. If you take these two pieces of information, a pair of prime P, Q, and their product, from an information viewpoint, they're obviously the same. You have one, you have the other. But if you are computationally bounded, you have this, you easily have the other. If you have, by assumption, this is impossible. So this connection is extremely informative, and we borrow a lot from information theory. We send a lot to information. There are lots of differences, and I'll show you some commonalities soon. What was the first mission of complexity-based cryptography? What these guys achieved in these seminal papers, like Diffie-Hellman, RSA, Goldwasser-Michali, is solving one problem, one cryptographic problem, secret communication between parties who never talked before, like Alice and Bob here. Alice wants to buy a book from Amazon. She never met Amazon before. There's a credit card involved. What do? Well, the problem is somebody is listening. So, well, no problem. You give, I'm not saying how, you give everyone an algorithm, an encryption algorithm that only he can decrypt. And that's exactly what Alice is using when she's sending her credit card that's on your laptops. And the reason it works is because of this theorem that efficient recovery of what's in this envelope here is as hard as factoring. If you do that, then you get factoring. This was the initial results. But what if you get partial information about that? This wasn't clear till Goldwasser-Michali made the right, I would say, standard for cryptography. It's not about finding out what you send. It's about distinguishing what you send from a random message. Once you have such a strong standard, then cryptography is a much more solid footing, and you can compose things, and lots of reductions compose, etc. And this proving such results is a new kind of reduction, because it's not reduction between two problems. It's reduction between some constraints of a cryptographic setting to solving a computational problem. But the upshot of this was just secret communication. So now we have secret communication. We solved the first problem of cryptography. What else can be solved? And now, came the fantastic 80s. I was a graduate student and then a postdoc here at Princeton and at Berkeley with Dick. He can't really cut me out. It was completely theoretical, completely intellectual game of inventing more and more challenging scenarios, which are obviously impossible to carry out, like digital signature, secret exchange, all these amazing things, and finding protocols for them. So for each one, somebody came up with a challenge, somebody else came up with a ingenious solution, which involved basically a reduction to factoring or to a similarly hard problem. So one thing you could say for sure, it was not clear where the structure is. So good. So there are lots of challenges, and lots of them we can meet. There are many more, of course, and I'm not telling you this. This is all in the span of 10 years. And then suddenly, boom, in a couple of years, we understood that everything can be done. Every cryptographic problem, whatever you can imagine, your wild mind can generate, can be solved. So let me elaborate on this. And this by unified reduction that I'll show you in 2 steps. And I want to highlight this zero-knowledge proof that Shafi talked about as a key complete problem, if you will. These are proofs which are convincing and reveal no information. Another paradoxical notion here invented in the really wild minds of Goldwasser, Michali, and Dracul. So what is the story with bad guys, with cryptography? There are 2 kinds of players in cryptography. There are bad guys and good guys. Both of them present problems. Bad guys are really, you assume nothing about. They're the real adversaries. They can behave in any way whatsoever. And, They are the good guys who will say what you know, there's a protocol, they'll follow it, but their ears are big. I mean, you know. And you don't want them to learn your private information. So this is about fault tolerance, resisting errors and malicious behavior, and this is about keeping your secrets even if players are behaving. So the two steps are eliminating the bad guys. So how we achieve everything? We eliminate the bad guys, and then we'll deal with the good guys. Okay? How do you eliminate bad guys? I'm not really going to tell you any detail, but basically, you know, once we prove that zero-knowledge proofs can be given to anything which actually has a proof, you know, that's not a big problem, because a bad guy has to do something which depends partly on his private information, but if he could prove in zero knowledge without revealing his secret that he behaved correctly, then, you know, we can force him to. So we are stuck now with good guys, and the question is, how do you solve many of these problems? Remain a problem even if everybody is good, everybody is benevolent and cooperates with the, you know, with the protocol. You want examples? There are zillions of them, but the most basic is elections. So even if, you know, you have players who want to decide something, and all of them do exactly what they are told, it's not clear how you will make sure that all of them learn the outcome, and no subset learns more than the values it contributes to the election. It's a serious problem, and you can think of a zillion others. So how do we deal with this? And this comes, here's the second part of this reduction to everything, is Yao's oblivious transfer. And it is another story of a reduction and a complete problem. So you want to compute some function, like majority function in the case of elections. And the you know, realization that should be obvious to all computer scientists is that, you know, you compute a function, it has a local computation, it has a computation in hardware, okay, with logical gates. You know, that's how, you know, whatever function it is you want to compute secretly, privately, etc., it has a circuit. But the circuit is composed of gates. So it's, a complete problem presents itself. If you could do one gate, just one gate, then you could do it all if you could compose it. And so this locality comes in again, and that's what Yao did. He said, well, let's try to compute one gate and do it in such a way that the computation will be oblivious. The values you are computing with will live in envelopes. The people could manipulate them without understanding them. And I'm not telling you what implementation he used, but it was not that difficult once you have the idea. Computation can go on as long as you like in envelopes, and when the outcome is ready, you just open for the benefit of all the envelope. So having locality of computation is the key to solving any problem. So here's this completeness theorem. Every task, whatever constraint, playing poker by telephone, even if players are good, is highly non-trivial, I assure you, can be performed securely and privately in this complexity theoretic setting. So this is the upshot of these years of research, and now I want to go back to this issue of information theory versus complexity theory. This is completely a complexity theoretic result. It assumes the hardness of factoring and the fact that players are limited. But there is a message here, right? What's the message? At the end of the day, the single primitive we used to ensure private communication, the most basic problem, was powerful enough to do everything. Now you can ask yourself, and we ask ourselves, what happens in the information theoretic world? Suppose we are in the information theoretic world, and by analogy, you know, maybe you have, you know, a bunch of players with private inputs, and now there is no cryptography, they are infinitely powerful, but they have private communication, they have private channels between them. That was the primitive that worked magically in the complexity setting. What can it do for you here? Well, it turns out everything. Everything. The proof is different, you know, and the technical issues are different, but the method, the very possibility that just ability to do communication privately will allow to do computation, any computation privately, I don't think would have arisen without this connection between complexity and information theory. So even this can be done. Okay, very good. So now I'm standing on 45 minutes. I'm measuring my time, Dick, so you don't have to even worry about anything. Okay, that was the end of the third vignette. I want to talk now very briefly about structure in randomness. Just a couple of slides, even though this was the topic I meant to talk about for an hour initially. That was my first title. But Christos liked the gospel better. One of the most powerful ideas that, we have in computation is the use of randomness. Much beyond, we use it in much more sophisticated ways, and of course statisticians use it, but much more sophisticated ways. And probabilistic algorithms are abound and are used for a variety of purposes in a variety of domains. These examples and many others are problems for which there are very efficient probabilistic algorithms, very efficient polynomial time, but even very efficient. And if you try to solve them deterministically, seem to require exponential time. Okay? Seem to require. So what's going on? So is this power of randomness real? That would be, and in fact was for a couple of decades, the gut reaction. Yeah, randomness is extremely powerful. But then things happen, and we managed to, at least for some of these problems, find ingenious deterministic algorithms. So at least for some of these problems, it seemed like randomness was exponentially powerful, but was not. What about the other problems? The other question is, these randomized algorithms assume the availability of perfect, independent, unbiased coin tosses. Where are they coming from? Is reality providing us with them? So let's look at these two questions. So I'll give you just the two results in 1 minute that I plan to elaborate a lot on. There are two, so perfect randomness, I grant you, doesn't exist. So even though John Preskill is here and will tell me that quantum computing or quantum mechanics predicts that you can get perfect bits, once you build a device for this, it will not be perfect. Even if it gets you, the bias will be within 0.001, it can ruin most probabilistic algorithms. So there is no perfect randomness. So one theory that developed over a quarter century, and I'm developing one line to it, is the theory of randomness extractors, randomness extraction theory, which tells you the following. You don't need perfect randomness for all these and any other algorithm. No need for perfect randomness. All you need is the entropy. The right amount of entropy suffices. If you need perfectly random bits, and you can get entropy n in some n-squared bizarre samples from, I don't know, sunspots, it's good enough. No need for randomness. So that's an amazingly powerful tool, which is actually used also in quantum computing and quantum information theory. So that's one situation, that there is some randomness. The world is inherently random, maybe, and we can't access these random bits perfectly, but it exists somewhere. That's good enough. We can run all our algorithms, and these are non-trivial, use of the randomness, because if you have entropy somewhere, you have to get it out somehow to be used by these algorithms. So all of this can be done automatically. That's one situation. The other situation is that the world is deterministic. Despite what the physicists tell you, we are in one big deterministic system. There is no randomness at all. So what do you do here? So what do you do with all these wonderful applications that we need? It turns out that also there it's no problem. You don't need randomness. All you need is one hard problem, any hard problem. So I write it P different than NP, but basically I know the traveling salesman is hard, or the permanent is hard, or something like this, would suffice to turn every probabilistic polynomial time algorithm into a deterministic polynomial time algorithm. No blow-up. And this is the connection, the wonderful connection between hardness and randomness. Good. So that's the structure we have here. We can eliminate randomness. And now I want to turn to the set story, which will be also short. So proving lower bounds. This is a failure. So the field existed for 50 years, complexity theory, 40 years. We want to show that any problem is hard, and we can't. We just cannot. And the situation, the structure here, I would say, is more or less like this. This is mood swings of a lower bound prover. Somehow, I don't know why, but even decades are good and odd decades are bad. So in the 60s, there was a bunch of lower bounds for Turing machines. And then in the 70s, people actually realized that all these techniques are bound to fail if they are going to prove P different than NP. Then in the 80s, we have the exciting decade of circuit lower bounds. And this was really wonderful. But in the 90s, Razborov and Rudish told us, look, all these techniques fall under what's called natural proof, and they are bound to fail. Actually, they are bound to fail only if factoring is hard. An amazing connection, but again, I can't elaborate. Again, because of interactive proofs in the 2000s, it turns out that these techniques were useful to prove other lower bounds which are not natural. And then it turns out that even these arguments have their shortcomings, and they cannot prove that P is different than NP. So, and I'm not sure what's happening in this decade. Nothing much is happening yet. There are other things we try to prove, lower bounds for cryptography, for learning, and so for average case hardness. And all the tools we have in these domains are more or less black box, and we can prove that they fail. So what is really interesting in all this story, well, first thing is I could say, where is let me add, is that what happened here in the odd decades and what happened here in understanding, what we are really good at doing, and I don't think people do it in mathematics. For example, the Riemann hypothesis is a problem that resisted attack for a long time, and everybody wants it to be solved. It's like the most important problem. So, okay, they can't solve it. They try and they can't. I would say that what we do extra is look at the techniques we have used to try to prove it, try to encapsulate it in some format, and say, look, we have to step beyond that. So introspection is, I would say, A, is more or less ingrained in us as computer scientists. B, is possible for us because proof is a computational notion. So we can encapsulate proofs in a computational model and argue about it in the same tools we use to argue about algorithms and about lower bounds. And that's in particular why these considerations lead to lower bounds in other domains like proof complexity, and even try to probe the question of the independence of P and NP. Okay, I decided not to spend time on open problems. They are obvious, nice. Well, there are many others, of course. The nice thing about open problems, I would say, in our field is they carry conceptual meanings, and that's one of I'm fascinated by this, and we can't prove anything, right? I mean, even superlinear lower bounds, we cannot prove that multiplication is harder than addition. So that's not what I want to devote my last slide to. I want to devote it to this. So, because I think the research in the field is going great. So there's no, visions about research. Just continue. Everything that was happening is great, both inside the core of TCS, outside. It's wonderful being a part of this field. So I want to talk about education challenges, and this call out to my colleagues and myself, I guess. Let me divide it to three. Clearly, I mean, this conference is a great demonstration. Algorithms is the language of the future. Everybody has to know to talk it, to speak it. So where does it start? We have to start basic education. And I think it's obvious, and in fact, there are attempts, everything I'm talking about, people are starting, and I think we should go about it in much bigger force. It should be another part as basic as math that should be added to the curriculum, and it takes serious development, but the reasons are obvious. I mean, kids will like it. Efficiency is natural to everybody, so trying to get efficient algorithms for problems is easy. Of course, there's great fun in algorithmic problems, so that's another bonus. Another important thing that was pointed out is that unlike solving algebra problems or trigonometry problems where, well, you got it right or you got it wrong, when you are trying to find solutions, there are better and better solutions that you may find to various problems, and there is a grayscale, and it's much better for students that this exists. And of course, there is, again, this conceptual meaning behind many of these problems that should motivate people better. Sometimes I would say that some weird stories about, I don't know, somebody climbing, well, let me not give examples, in word problems in math, 2 trains and so on. Okay. In the college and graduate school, I would say for TCS, the real challenge is, it depends on money, of course, and is increasing the numbers, because what, you should all be observing, everybody, all of us have been observing, is this fact that there is a huge draw on the talent of people who can do computational modeling and algorithmic reasoning in all these sciences. And at the same time, standing at the core in the basement, there is a growing need of talent to work on these, some of the problems that I mentioned. I just believe that we need to produce more people with this understanding and abilities. And finally, for the general public, I have just one hope or wish, and I don't know how it will happen, is that Turing will become, the household name it deserves to be. Thank you. It implies that BPP equals P. So let me repeat. Again, one hard problem, let's say satisfiability or the permanent or some p-space hard problem is very hard for circuits, implies that every probabilistic algorithm, polynomial time algorithm, has a counterpart which is deterministic. This is it. All of them, you don't need the randomness at all, up to polynomial factors. So again, once you start worrying about real efficiency, but within polynomials, no loss. No need for randomness if you have a single hard problem.
With respect to your very last slide, do you have any advice for the vast sea of implementers of algorithms, software engineers, and those who feel a responsibility for the profession? Software engineers struggle with from your point of view. On one extreme, they're sort of the algorithmic-less cowboys that do things.
Right. So the question was about the educational slide and whether software engineers can help in this regard. I think that software engineers can help a lot. What I was trying to stress is conveying the mathematical or the theoretical underpinnings of computer science. Many of the ways to do it right, which are used in colleges, is aiding them with software that Bob Sedgwick, for example, has a great project in which algorithms are taught and people are seeing evolution of algorithms and how, different algorithms are, relate their efficiencies and things like this. But I was really focusing on making a really robust and attractive curriculum to students from very young age. In fact, there are several proposals. I don't want to talk about it too much, but several proposals for playing games even with very young kids with coloring graphs or with cryptography that will start. I mean, you have to just start speaking the language, getting familiar with the concepts before you formalize things, and then maybe in high school formalize. But I think that seriously, doing things efficiently, solving problems efficiently is so ingrained in everybody. I mean, just save time doing your homework and then running out to play with your friends. You want to get it out quickly. So, yeah.
One more question somewhere?
Yeah.
How many 1,000 square feet in the basement do you guys need? We are innovating the
I think just below the peace room would be just fine.
How deep do you want it?